gain anyone. The blue side does not gain any ground, right? So they're just losing people. What? Oh, I have some trouble with this. Okay, so now after day 1, you can see day 2 is even worse for the blue side, because here you already see that 20 is in trouble. 17 and 18 and 14, they just barely hold there, right? They have no chance to survive. I mean, in the sea of red. So this guy just died. So after day 2, there's only 21 holding, but not for long. And then day 3, the red wins totally. Okay, so that is one example. Now the second one is actually more interesting in some sense. Now the graph still have 25 vertices, but now there's no zero guy in the middle who sort of held every other red. The game is slightly more balanced. Like okay, the blue is still pushed to the boundary, and the red are more connected in the middle. So you can feel that the red have some advantage here. But let's see how the game play, right? So in the first day, actually the red winning 18, right? It win 21. They also win 15 and 12. The blue side fight back a little bit, and then they get number 3. So 3 change from red to blue. That's the only guy that the blue side can win. But you can see that the number 3 will be in trouble already the next day, right? And then so is 16 and 17 and 19 and 20. They are surrounded by red. So you can feel that this game sort of may end the same way as before. Yeah, but not. Yeah, so let's go to day 2. And you see that the number 3, as I said, he was in trouble. So he become red. Actually, blue win back 15, quite strangely, but it win back 15, and then it actually keep the older guy on the down, the right corner here. Now in day 3, actually the guy 3 start keep switching sides, because it have now 3 blue neighbors and only 2 red neighbors. So the 3 come back to be blue. And the next day it come back to become red. That's the trouble guy. But after that, you can see that nothing changed anymore. The game come to a stalemate. That blue, although outnumbered by red by a factor of 3, it they keep their front. They do not lose any more people, and this will be the more or less the end of the game. Yeah, so you can see that the end of the game here also ended in one position. Nothing will change, but in this position, both red and blue have some colors left. Now number 3 is an even more interesting graph. It is graph, when still as a beginning, red have a slight advantage. So it's 13 and blue have 12 as before. After the first day, you can see that actually red seem to be winning. It takes most of the guy at the boundary, like 16, 17, 18, 19, 21, 22. And then, so 20 is in deep trouble already. On the other hand, blue gain back some, some ground, like at 6 and 5, and also 4. And then somehow in this region, it gets number 12 as well, although it's losing number 13. So it's sort of a more interesting game. Like there are really a fight here. So red wins some and blue wins some. So here is the game after day 2. Actually, it seems like red is winning because, you know, it already gained some ground on the first day, and in the second day, only 6 blue is left. And actually, they are in deep trouble. Like 16 or 17, you can see that you are losing immediately. And so is 13 and 14. So, yeah. And the only guy who seems to survive is 23 now. Interestingly, although the blue side will lose all of this guy, like as I said, 16, 17, 22, it gained back a few, like number 12 here, or number 24, or older guy at this corner, the 4, 5, and 15. So it doesn't want to lose so quickly. So here's a picture at day 4. Actually, it loses this guy, 5, 4, and 15, as you see. Although they have 5, 4, and 15 at blue here, all of them are in trouble because they are surrounded by red. They don't even have any blue, you know, neighbors. So you lose all those guys, you gain back a few. And now to day 5, actually, you have this position like 4, 15, 12, 23, 24. So very interesting thing happened. Like after this, you see that you lose. You have 4 and 5, you lose both of them, you get 16, right? And then you have 12, 24, and 23, you lose both 12 and 24, but you gain back 13 and 14, right? And you get back 22 as well, because you have 12 and 23 here. And now you see that actually it's periodic because you have seen this picture before, right? You have seen this picture in day 5 already. So, well, when it's periodic, it will keep become periodic, right? And now you see a different, you know, ending of the game. So we see the game ending with one side winning everything. We see the game ending with, you know, both sides retain some colors, but nothing changed. And we see the game ending with a period 2. And there's a theorem actually proved by 2 groups of people, Gauss and Olivos and Poyak and Sura in the early 1930s, saying that those are the only ending you have. Either you have a stable ending or you have a 2 periodic ending. There's no period 3. Right? Okay, so that's a nice theorem saying that, you know, what would happen. Okay, so now, well, we do what we do. We consider this game on random graphs, of course. Now, if we have a random graph, say G and half, and we start with, you know, a red and blue with the same size, say n over 2. So the way I see it is that I first partition the vertex set into equal set, red or blue, and then I draw the graph onto that vertex set with the partition given, right? So because of symmetry, the probability that red win have to be the same as probability that blue win. Now, of course, now if I give some advantage to the red part, then red is more likely to win. And the question is that how much advantage should I give so red win with probability close to 1, say 90%, right? So the fun application in my eyes is that, okay, we have an election which is tied at the beginning, and you want to bribe a few people to make sure that you win, say with probability 90%. And okay, how much does it cost you? So that's a real life application, and should sell it on the broader impact part of NSF grant. It's have a huge impact for sure, very broad. Okay, now of course it depends on the answer. If you have to bribe everybody, then nobody want to apply it, right? So they want to reduce the cost. So this is the question that we investigate and we want to answer. Yeah. So there's a few ways to yeah. So as I said, the model you have I have in mind is I fix the vertex set and draw the random graph on it. In some version, which I will not consider in this talk, we also have an online rate. So actually the graph is actually the internet, and it will not be online every day. It will be online maybe on half of the day, or maybe 90% of the day, depending on how much you go on Facebook. And then the game will be considered only for those people who are online. So we have that version as well. But I will not focus on that. Yeah, but we can make many models on this to make the game more real. Yeah, I also have a version about chat room. When I am online, you are online, and we are connected, so they are correlated events. But for the sake of this talk, I just do GNP. All right. So there are a few equivalent definitions that sometimes more convenient to consider when you want proof result. Like you can first generate the graph and then choose the red part uniformly from every set of n over 2 plus delta vertices. Right? Or you can fix the partition first, then generate the graph, and then choose a random subset of delta blue and let them defect to red. Right? So like you bribe delta random person from the other camp. So you don't have to go to the very influential people or the rich people to bribe them. They are expensive. You just go to a random guy, you bribe them, and that works. Right. Yes, so all these things are equivalent because they generate the same probability space. Okay, so now the power of field phenomenon is this. So we say that the color wins if at some point that color is the cover the whole graph, right? So everybody, voted for Trump. Say, well, it's not a good example, but yeah. So the question is that in our random setting, how small delta should be, can be, how small delta be must still guarantee that red win with say 1 minus epsilon probability. So this question have many variants and precise version and have been recently studied by many group of people. Some of them here, and you already heard the talk of Jong Han. There's the work of Futulakis, Khan, and Mackay that we will discuss, and some recent work of Devlin and Berkovich and Shah and Sony as well. So it seems to pick up some steam, and there's still a lot of open questions to attack that I will mention at the end. Yeah, so the power of field phenomenon is this. Winning is cheap. You need only to bribe a few people to guarantee a landslide win. Good news for people having my theorem in mind that they can go and and the point is that the number of people you need to bribe doesn't depend on M, the population. It depends only on the density of the graph and the winning probability. So let's say P is 1/2, and you want to win with 90% chance, you have to bribe only 6 people, 6 random people. Really cheap, right? It doesn't matter that your population is 1 million or 100 million, and 6 can be even reduced. But I mean, it's already small enough number that you can do it in real life. Not I suggest that you do it, but you can. So the theorem is this. Yeah, say it's a toy theorem for just G(n)(2). If you start with n over 2 plus 6 red vertices, then it will win with probability at least 0.9 within 4 days. And the theorem already applies for n larger than 300. You don't have to let n go to infinity and 1 over log n go to 0. Nothing like that. It's applied for small number. So we can go to our village and apply this.
And can I ask you a question?
Yes.
Is there a computational aspect of this? Do you know how to find, let's say I tell you 50-50 and then you're allowed to bribe.
Yeah.
You know how to find them?
I just bribe the 6 random person.
And if you want to guarantee a win?
Guarantee like 100%? Oh, that I don't know. I mean, we don't want too much. 90% is good enough.
No, but other than choosing them at random and seeing what happens, do you know how to select an efficient?
You mean if I say, well, we can pose a question like this. I don't know if it's what you want to ask. If I select the best person, will it be better than select a random 6 person, right? Yeah, so maybe random 6 give me 0.9, maybe the best 6 maybe give me 0.94, right? That's the question. Then in that case, I don't know.
No, you can imagine another theorem which says in GN1/2, if you give me a 50-50 partition, I can sway 6 people and win.
Oh, I think that's probably not enough. Yeah, I think 6 will not give you 100%. Yeah, I think we can prove some lower bound. Yeah,
and it goes to infinity in that form.
Yeah, I think it should go to infinity if it 100%.
Thank you.
Yeah, so there are a lot of questions we can ask here, like a random 6 is better than the best 6 or not? And I think the answer is no, but yeah, this is so in general, if we have constant p, then actually it's the general theorem. The 1/2 case, just a corollary, and then we would win in the same 4 days. Well, delta is something like 1/√p or something. Yeah, so here you can compute the probability of winning as 50 divided by the minimum of n and p times delta squared. And so it applies already for n very small as well, right? N is 1,000 already give you something pretty good. Yeah. So that is the phenomenon that somehow surprised me first when we find it. We first do a lot of experiments to see, and already delta equal to 2 give us something quite significant. I mean, close to 1 already. So that's how we make the conjecture, and then when we prove it, that's not too hard to prove, but somehow it's surprising to see that this thing is true. So I keep asking people from various disciplines of sciences, like mathematicians, computer scientists, and people in chemistry, etc., or people in economy who propose the question actually, and all of them have a wrong guess. The only guy had the right guess that delta could be a constant. To get 90% is the physicist, because he works on percolation. So he knows this, long-term effect phenomenon. That's sort of similar. Okay, so let me tell you the intuition behind this, and then okay, I will not prove anything, but the proof have numbers in it, which I don't like. A lot of numbers. But basically, the intuition is very simple. Once we think about it, we consider, say, a vertex V at day 1, and assume that, okay, we have n/2 plus delta red guy. So the number of red neighbors of V, now we expose the graph, right? We expose the edges. Will be roughly, well, I cheat a little bit here, but it's roughly a binary distribution with, n/2 plus delta 1/2. The number of blue neighbor is the same, but the mean is down by delta. So by standard deviation, because the standard deviation of both things are square root n, and we can assume that they are more or less independent, the probability that x is bigger than y is roughly 1/2 plus delta times n to the minus 1/2, right? Because you gain delta in the middle of the standard deviation, period. So each of the points in the standard deviation give you 1/√n gain. Now, because of this, and by expectation, you can expect that in the next round, the number of red will go from n/2 plus delta to n/2 plus delta times square root n. Right? So the advantage is blow up by a factor square root n. And now if you repeat the argument, of course, repeat is in here is in quotient mark. With the new delta replaced by delta times square root n, and in the next round, your advantage would be linear, right? Because you multiply by square root n twice. So you will have like 0.6n versus 0.4n. But once the advantage is linear, then you just say that, okay, the bigger guy will win by check no bow or any kind of very easy argument can do. Now, of course, the point is that it is not so easy to repeat the argument because you have the right to expose the random graph only once, right? You expose it's here, then actually the next step, there's no binary distribution anymore. So you have to, play some game to say that, okay, after the first round, we still have enough randomness left to do something and that sort of stuff that, people here do a lot. Well, we make a living out of it, but that's okay. Okay, so now there's some quite interesting recent refinement. So we sort of convinced, or we really think that this phenomenon is nice. So we can refine it a little bit. For instance, the simulation show that even for delta equal to 1, the minimum advantage that already give us a probability, a winning probability significantly larger than half. I think it's something like even close to 0.9. So we make this power of 1 conjecture in our original paper 3 years ago that even the minimum, advantage is guarantee a non-trivial, winning probability. And if n is not odd, I mean, I always consider the version n over half plus delta and n over half minus delta because I really like this bribing thing, like, okay, 2 equal sign and I start to bribe your people and delta of them joy and then I win. But if n is odd, you can think of, okay, one side is slightly bigger than the other side and say r minus b is 1 and exact all the argument will repeat itself. There's no big difference between the two cases. So their result sort of confirming this conjecture. First of all, Devlin and Berkovich show that delta is 1.5 surface. That means red minus blue equal to 3 is good enough. Already give you something like 0.6 or 0.7, I don't remember. And then Shah and Shawnee proved the conjecture in the precise form when they can compute the probability that red wins for any given delta. So it depends on Phi's distribution function for the Gaussian, and then you can compute precisely what it is. And it did go to 1 very quickly with delta. So there are the recent refinement of this. Now, okay, so now because we are talking random graph here, then okay, so we have to go threshold, right? And what about general P? So we know that the connectivity threshold is log n over n. And if P is smaller than log n over n, then it will have a lot of isolated vertices. So no size. And so in the beginning, half of the isolated vertices will be red and half will be blue. So you cannot expect to win. You cannot expect to attain anonymity anyway. So the question naturally is that what happens if P is bigger than log n over n? So do connectivity and anonymity share the same threshold, right? And yeah, so there's again, I said there's an online version as well, but I will ignore this. So there's this letter Q coming in at certain point. It's an online version when everybody will be online with probability Q. Okay, so the new theorem we have is sort of solve this question in some sense. So yeah, so ignore Q. We stated Q equal to 1, or you can think of Q as something like 1/2. Every day, half of the people will be online. So if we have these two conditions that P times delta is bigger than 30, and P times n is bigger than log n, which is just the connectivity threshold thing. So the condition on delta is something like delta bigger than 30 over Q over P, right? Then we have this. We have the theorem very similar to the one we have for the constant case. So exactly the same form, the probability that red win is 1 minus 50 over the minimum of n times p times delta square. And the number of days for winning is order log n at most, but typically it is constant, which you can compute from, well, there's a lot of parameters here, the p or the q and the lambda, but ignore them. The message is that once the graph is connected, then red is going to win, given that delta is big enough, say a big constant divided by p. Okay, so now let me discuss two things, some related work on slightly different models, actually what Jong-Han discussed, and then a lot of open questions. Okay. Any other questions so far?
I have a very...
Yeah. I think we lose your voice.
Oh, really? Oh, I thought that I have a voice. But then
Okay, now it's good now.
It's good. Yeah, question is, this is just, can I understand it as a side percolation on GNP? Can I understand that way? With the probability Q, I'm there. So this is a, can I interpret it as a side percolation, right?
So the way we interpret it is that, yeah, it will be online. Maybe every day half of the people will be online. And when they are online, they see everybody else. They can see the offline guy. They can also see the
kind of side percolation, I think.
Yeah, exactly.
Thank you.
Thank you. That's what you mean.
Yeah,
right.
Then I understood. Yeah, thank you.
So yeah, I have one more question, man.
Yep.
So you quoted these old theorems from the early 80s that either one wins, either or a stalemate or a cycle of two.
Yes. Yes.
So how likely is given as a random graph to even?
Yeah, that's a great question. So I will have a lot of open questions related to that. As far as I know, there's no clean characterization for which graph ending which case. Yeah. So we don't have a good characterization for that. So there is another setting which have been studied by many group of people, which I mentioned at the beginning. So here the coloring is also random. Namely, in the beginning, you color each vertex red or blue with probability say 1/2. Now you see that in this case, delta is just by standard deviation is already of order square root n. So the assumption is stronger than what we consider. So by conditioning, we can derive some of the existing theorem in the literature from our theorem, because we have big delta here. There's another setting when we can give, say, red a little bit advantage. So you can be red with probability PR and blue with probability PB, which is 1 minus PR. And then we can also study that situation as well. Okay, so here's the theorem of Luckykang and Mackay a few years ago. If we have P, say big enough, say bigger than a big constant times 1 over square root n, and you have a balance, a coloring at the beginning, balance mean PR equal PB equal 1/2, then the larger side in day one wins with high probability. Right? And as I said, by conditioning, we can derive this theorem from our result because the larger side would very likely have square root n advantage. The version will be a little bit slower in the sense that it will not be 4 days, it will be something like 15. But the proof is very easy. So by central limit theorem, you just say that with some probability close to 1, like 1 minus epsilon over 2, then delta will be at least some constant depending on epsilon times square root n. And then we just apply the theorem that we have. because in this case, P times delta is bigger than 30. That's what I say. It's important to notice here that the probability P is big enough compared to 1 over square root n. So if we get this condition, then we are fine. Now, the interesting thing that Jong-Han talked about the other day is actually reached below 1 over square root n, right? So they say that now here below 1 over square root n, what Jong-Han talked about is n to the minus 3/2. Then our condition, of the theorem doesn't apply. But still, the larger side would win. Now, not 4 days, but 6 days. So this number of days are mysterious. We never know which is the right one. That's the Kim, Charabotti, Kim and Lee and Chen result. It's a different Chen, by the way. So it's motivated by the conjecture of Benjamini, Chan, and O'Donnell, Thomas, and Tan 5 years ago. And they say that if for P, the density of the graph is superior to 1 over n, then the larger side will cover almost the graph, but not everything, but 99%. The reason being that, okay, you will have isolated vertices and stuff like that. It will not cover everything. Yeah. But in the range, when the graph is highly connected and cover 99%, will imply that cover everything. So basically, this result of Chakraborty, Kim, Lee, and Chen confirm this conjecture for the given range of P. So I think Jong-Han talked about this already. Okay, so another interesting aspect is that close to the connectivity threshold log n over n. If we want to win, then how much you should increase PR, right? So if PR is 1/2, then actually you win with probability 1/2. But now you increase PR slightly, then what would happen? So in this case, there are also very quite recent result of Zemakan saying that above the connectivity threshold, you increase PR from 1/2 to 1/2 plus 1 over square root of PM. Then you are winning, right? Yeah, but you can prove similarly by just simply conditioning from our recent result, the more recent one, the 2021. The later paper is that it's enough to replace 1 over square root 1 over square root Pn by 1 over square root n or 1 over Pn. So it improved this theorem again in the slower sense that the number of days you win is now may blow up to log n. Right? So okay, so the proof is the same as before, just conditioning. Now come actually a lot of interesting questions, I think. Okay, I have only like 5 minutes left, so I will be fast. But yeah, so here's one. If we are balanced, delta equals 0, what happened? So the current result of Shah and Sony show that when the graph is really dense, then the side with more vertices after day 1 would win. So you have the game, you start with balanced picture and you have the game ever for 1 day. And after that, the guy with more, more people will win. And we conjecture that it will be the situation for anything above the threshold, not only very dense graph. Second, what happened below the threshold, but still big compared to 1 over n. And we do a lot of, numerical experiments here, and the conjecture is that if it is c times log n over n for any constant t c less than 1, then one guy will win on the giant component. The other guy will have like some power of n vertices, but we don't know what this power is, right? Yeah, so for the sparse case, there's this. Now, what about the range when not connectivity, but the giant component range? So we do experiment for, P something like 2 over n, 3 over n, and so on. Now, interestingly, now the example at the beginning of the talk come back, actually, you see a 2 periodic ending. So the game would end with the 2 periods. And actually, not only that, both sides have nearly half of the vertices. Yeah, so on the giant component. So this is purely numerical experiment, but we make a conjecture anyway that on the giant component you will get a stalemate of periodic 2, and each side will have half of the vertices. Now, what about below the giant component? It's very easy to see relatively. Okay, we see that the game ends globally with a tie when each side have roughly n over 2 nodes, because now it's only the game on very small components. So the component, most of them will be trees. So there's some, we make experiment on this tree, and so the question here is, what is the game ever? What is the game on the tree or a random tree? Right. So here that we don't really understood them fully either. Okay, so to end I come back to the major question of the power of field is the remaining quantitative question after we discover the qualitative phenomenon is that given 1 over epsilon, right, and p, what is the minimum value of delta? So we want to win with probability 1 over -1 minus epsilon, and the density is p, and so the result of Shaw and Shawnee give the exact answer for this, for constant p or even p bigger than some power of log. But in general, we don't know, and the conjecture here would be delta is some constant depending on epsilon times 1 over square root of p. And if we have this, and actually you can answer the question of Benjamin et al. For the whole range of p as well. So this is the final conjecture I want to make. Okay, so my time is up. Yeah, thank you very much.
Thank you for the interesting talk. Are there any questions?
About your conjecture 3, I think in 2 pages before.
Yep.
Yeah, that was by these 5 people, right?
Oh, it was already appear there?
Yeah, I think so.
Oh, okay, then I will double check. Yes. So
Yeah.
Okay, great. Thanks.
No problem.
You gave us this Facebook example as one of the key examples that you can bribe small number of people to change the outcome.
Excuse me?
I like this theorem that you can bribe only small number of people to change the outcome, let's say on the Facebook network. But the Facebook network doesn't look like a GMP, right? So you want to have a sort of different graph model.
Exactly, right. Yeah, that seems to be a very interesting question. So we can sort of go to a random regular graph and stuff like that, but they are of course very fake model for real social network, and it just makes the problem harder and mathematical. Yeah, but the real one is more like model of preferential attachment graph that people have long time ago, or small one graph, or one of these graph people claim to be the right model for the real one networks. How much we believe in this is another question. But anyway, in that case, of graph which are inhomogeneous like that, right? So if we take the model of a preferential attachment graph, then all the vertices that coming at the beginning, they are very important, right? So they are not homogeneous. And so the theorem would have to read like, okay, you have to weigh these vertices somehow. Like, if you bribe the guy who are at the beginning, then it would cost more than you bribe the guy who are number, square root n. And then we go that way. But it's not clear to us how to make it quantitatively convincing yet.
I see.
Yeah.
All right.
I wanted to. Sorry, I only wanted to point out.
I have some weighted version of the theorem, but they just look too ugly to apply to anything. So yeah. Oh, by the way, yeah. Please.
Just wanted to point out the connection with a different line of research. I'll only mention it. An external partition of a graph is one where every vertex has at least as many neighbors on the other side as on its own side. Every graph has such a partition. Internal means that every vertex has at least as many neighbors on its own side than on the other side. That doesn't always exist, but there are lots of conjectures and theorems that say that usually most graphs in a very strong sense have such a partition. And I'll see that such an object is exactly a stalemate. So there is a whole literature on this thing, not as big as the one that you described here, but it would be interesting to see if there are any connections between these two areas.
I see. Yeah, of course. Yeah, yeah, exactly.
I have a paper with Amir Ban if you want the pointer to.
Sure. I mean,
Nati, can I mention something?
Oh, sure.
So I think you mentioned this Bella-Bolobash is a conjecture or type. Indeed, the Matthew Kwan was visiting graphs and we were discussing indeed exactly the two problems using some method. And it turns out that at least we use so-called warning propagation algorithms. From that point of view, it has a little bit of similar flavor because it has to do with tie, how you have to handle the tie vertices. So in some sense, there is indeed a strong connection between these two, indeed, as you pointed out.
Mm-hmm.
Maybe,
right. In the analysis, the tough matter is how to deal with these tie vertices, indeed. So indeed, in that sense, it's really related, this problem and this neighborhood or friendly or unfriendly partition problem.
Right, so we have to conclude the start. So let's thank the speaker again.
Okay, thank you.